Hi, so let us solve some problems on solid fuel combustion. Case 1. Given a furnace is fired with high volatile bituminous coal whose ultimate analysis shows 75.19% carbon, 5.19% hydrogen, 8.72% oxygen, 1.5% nitrogen, 7.8% ash, and 1.6% sulfur. Air is supplied with 60% excess over the theoretical amount. Assume that CO to CO2 molar ratio is 0.175. The stacked gas leaving 300 degrees Celsius and at 740 millimeters of mercury. You're asked to calculate the complete analysis of the stacked gas if air is supplied at 28 degrees Celsius and 100 kilopascal, essentially dry. B. Volume of air supplied in cubic meters per 100 kilograms of coal. C. The calorific value of the coal. D. The percentage calorific value lost due to unburnt combustible and uncondensed water from combustion. Also given here is a calorific value table of some of the fuels as well as the enthalpy of water. So we're given here the one on top. I just placed them here. I also drew already the process flow diagram. So let's just label the process flow diagram. So for this one, it says that fuel is coal, and then it's comprised of carbon, hydrogen, oxygen, nitrogen, ash, and sulfur. So carbon is given as 75.19%, and then this is 5.19, this is 8.72, nitrogen is 1.5, ash is 7.8, and this is 1.6 sulfur. So since this is solid fuel, this one would be percentage by weight. I'll just erase the percent in here. Okay. Also, what else is given? For the air, you're given the conditions 28 degrees Celsius and 100 kilopascal, 60% excess. So air is 60% in excess at 28 degrees Celsius and 100 kilopascal. And then the product gases, this one would be the stacked gas, leaves at 300 degrees Celsius. So this one, and 740 millimeters of mercury. So the stacked gas would consist of CO2, and then here you're given CO2 to CO ratio, so CO2 CO, and then let's assume since there's sulfur, there's SO2, there's oxygen, there's nitrogen, and of course water vapor. What else is given to us? CO to CO2 ratio, so CO to CO2 is 0.175 for every 1. Okay, so let's write the basis. In here I can see that the best basis would be 100 kilograms of coal. So if we would have 100 kilograms of coal, what can we solve for first? First, we can solve for the theoretical oxygen. So let's solve for the TiO2. Theoretical oxygen would then be, since everything is given in terms of mass, I'd say C over 12 plus H over 4 plus S over 32 minus O over 32. So this one would be 75.19 over 12 plus 5.19 over 4 plus 1.6 over 32 minus the oxygen that is in the fuel. So that's 8.72 over 32. So everything here becomes moles. So this one is 7.342. This is the theoretical oxygen, or the oxygen needed to complete the combustion. Now, it says there that excess oxygen is 60%. So that means excess oxygen is 60% of the theoretical. So that's 0.60 times 7.342 is actually 4.405. By the way, this is in kilomoles already because our basis is kilograms. Therefore, I can say that the O2 fed, or O2 from air, is actually the sum of the theoretical and then the excess O2. So this is 7.342 plus 4.405. This is actually 11.747 kilomoles. Since we already have O2, we can solve for the amount of nitrogen from air, or nitrogen fed. So we say N2 fed from air, this is actually 11.747 times the stoichiometric ratio of nitrogen and oxygen in air. So that is 21 parts oxygen and 79 parts nitrogen. You'll have 44.191 kilomoles. Therefore, if I would like to have the total nitrogen, it would then be total nitrogen that would go to the stack gas. That's actually nitrogen coming from air plus nitrogen from the fuel. So that is 44.191 plus the nitrogen from the fuel, which is 1.5. However, since that is N and then this is N2, we divide by 28. So this gives us 44.245 kilomoles. So looking at this one, we already have the nitrogen. So let's try solving for the carbon dioxide, carbon, and then the rest. Do take note of this relationship. For every 0.175 CO, there's 1 CO2. So C going to CO is actually, we have in here 75.19 kilograms of carbon divided by 12. This becomes kilomoles of carbon. However, when you look at this, all in all, you'll have 1.175 parts, because if there's 0.175 part of carbon monoxide and 1 part of carbon dioxide, the total parts is 1.175. That's why in here, you would want 1.175 total number of parts, and then on top, that's 0.175. That's CO. Basically, this is CO over CO plus CO2. That's the ratio. So here, this gives us 0.933 kilomoles. And then solving for the carbon, that yields carbon dioxide, I can just say 75.19 over 12, but then instead of 175, this becomes 1 part over 1.175, because this now is CO2 for every CO plus CO2. So you can do this, or you can basically just subtract the 0.933 from 75.19 all over 12. You'll be able to get the carbon dioxide, but there you'd be able to get this one is 5.333 kilomoles. So now we were able to solve for carbon dioxide and carbon monoxide. Now we need to solve for the sulfur. We also need to solve for the oxygen. So for oxygen, let's try solving. Let's solve for the free oxygen. So the free oxygen here would then be the excess oxygen plus the oxygen that is used to convert the carbon monoxide to carbon dioxide, because carbon monoxide hasn't fully combusted yet. It was not a full combustion. Therefore here, it would then be excess O2 plus O2 to convert CO to carbon dioxide. So this one is actually 4.405 plus carbon monoxide is 0.933 divided by 2. So this one gives us oxygen of 4.8715. So now we have oxygen. All we need to solve for is H2O. The H2O from combustion, basically, all of the H here was converted to H2O. There's no H2, so we can solve for H2O from combustion. That's basically equal to 5.19. That's H, so divided by 2, you'll get 2.595 kilomoles. So I have created here a table for the stacked gas. So let's just transfer here the values. For CO2, we have 5.333 kilomoles. For CO, 0.933. For SO2, all of the sulfur will convert to SO2. Right? So this one, just divide this by 32. So what's 1.6 divided by 32 is 0.05. And then O2, that is 4.8715. Nitrogen, total nitrogen is 44.245. And lastly, water is 2.595. So when we total this one, it gives us a total of 58.0275 kilomoles. So getting the percentages of each, they'll be 9.19%. This is 1.61%. This one is 0.09%, 8.40%, 76.24%, and lastly 4.47%, which should give you total of 100%. So this is the stacked gas analysis. Next, you're being asked to solve for the cubic meters of air per 100 kilograms of coal. So air is composed of oxygen and nitrogen here. So the air is basically just the N2 from air, or N2 fed, and then the oxygen from air. So that's 44.191 plus 11.747. So that's 44.191 plus 11.747, because it says it's essentially dry, so there's no need to solve for water. So this is your nitrogen from air. This is your oxygen from air. And then let's do the proportion. So 22.4 cubic meters for every 1 kilomole. And then the pressure and the temperature correction. So here you'll have 273. And then what are we given? We are given 100 kilopascal. So for every 101.325 kilopascal, that's 100 kilopascal. And then you're given a temperature of 28 degrees Celsius. So that's 273 plus 28 all over 100 kilograms of coal, which is our basis. So solving all of these, this one would give us 1399.83 cubic meters of air per 100 kilogram of coal. So this is your final answer, which is actually the same as here, letter B. And then 1.61, 0.09, 8.4. So we basically have the same 8.4, 76.24. Yeah, so our values are correct. Next, so for letter C, you're asked to solve for the calorific value of the coal. So let's go to the Dulong's formula. This one is basically 0.338 times the percentage of carbon, which is 75.19, plus 1.44 times the percentage of hydrogen, which is 5.19, minus 1/8 percentage of oxygen, which is 8.72, plus 0.094 times the percentage of sulfur, which is 1.6. Again, this one here is actually your net hydrogen. So that 1/8 there is actually the proportion of oxygen and hydrogen. So that's 2 for every 16 parts. So here, all in all, you'll have an answer of 31.472 megajoules per kilogram. So this one is your answer. So let's check if the answer is correct. 31.472. Next is the percentage, the calorific value losses in terms of percentage due to the unburnt combustible. So when you look at this one, the only unburnt here, the only incomplete combustion is due to the carbon monoxide formation. So I can see here that the percent CV loss due to the CO formation is actually equal to, in here, you're given the heats of combustion, so you get the negative of that. So the carbon monoxide formed is 0.933 moles. So that's 0.933 moles times, let's get it here, 282.99 all over, you have 100 kilograms of coal, and the calorific value of the coal is 31.472. So all in all, the answer is 8.8 39% of the calorific value is lost due to the CO. Next is due to the uncondensed water vapor. So percent CV loss due to H2O. So in here, you'll have how much water was formed. 2.595 from the table, so that's 2.595 multiplied by here 44.013 divided by 100 kilograms, and then this one is 31.472. So the final answer would be, so that is 3.63% lost due to the uncondensed water vapor. So let's see if our answers are correct. 8.39 and 3.63. So that's 8.39 and 3.63. So I hope you understand my solutions. Good luck in solving. Thank you very much.